Hello, my name is Eric Zachariah, and my area of research deals with the hydrodynamics of caudal fins. This presentation will provide you with a brief overview of what I've been up to this summer in regards to the REU program at Syracuse University. For the month of June, I worked in the Center of Excellence, which is down the street from Syracuse University's main campus. Here my duty was to provide a helping hand to PhD student Justin King as we prepared a large water tank for future experiments and data collection. The preparations consisted of cleaning the channel of all dirt and residue, followed by constructing a mechanical support for the laser machine, high-speed cameras, and pitching panel. The plan for the summer was to acquire information about the flow behind a trapezoidal-shaped panel that pitches back and forth through water. Unfortunately, there were a few unexpected problems that occurred, which led to a lot of downtime. Fortunately, this downtime led to me beginning my own research project. For the month of July, I was able to formulate a plan for my future research goals and get everything set up and ready for the water channel in Link Hall, room 280. Hydrodynamics is the branch of science concerned with the motion of forces acting on or exerted by fluids, and a caudal fin, or tail fluke, is the tail fin of an aquatic mammal. The inspiration for my project comes from observing the fascinating locomotion of fish and aquatic mammals in the ocean. Specifically, dolphins, sharks, and whales are some of the ocean's most powerful and efficient swimmers, and studying their propulsive abilities could potentially lead to more innovative ways of nautical traveling. My research project branches off from Professor Melissa Green's Unsteady Swimming and Flying Flows research project. This is the same project that PhD student Justin King is currently working on. After acquiring data on multiple planes throughout the test section, Green and her students were able to create a visualization which was created using experimental data of a trapezoidal-shaped panel that pitches back and forth through water. The visualization displays the contours of positive and negative time, Lagrangian coherent structures, and vortices being shed off the trailing edge and tips of the panel. Like many engineering researchers use wind tunnels to study the aerodynamics of airfoils, I use a water channel to study the hydrodynamics of many differently shaped caudal fins. My experimental setup for the water channel in Link Hall is similar to the setup for the water channel in the Center of Excellence. The two major differences are the process in which we collect data and the overall size of everything used in the experiments. Justin King uses stereoscopic particle image velocimetry, or PIV, using 2 cameras for depth with a large water tank, and I use flow visualization by planar laser induced fluorescence, or PLIF, and 1 camera with a much smaller water tank. With that said, my experimental setup consists of a water channel that has variable flow speeds, a machine that emits a laser sheet through the test section of the water channel at various heights, test pieces that replicate the geometries of existing aquatic mammals' caudal fins and can be easily attached and removed from an Arduino-controlled RC motor, a fluorescent dye that is induced into the flow upstream from the test section, a high-speed camera that is able to record the flow and collect data from it frame by frame, and a support structure that can hold all of these things steadily and in a level position. I was able to create physical test pieces that replicate dolphin flukes using the following series of techniques. First, thanks to researchers at Lehigh University, I was able to recreate dolphin geometries on MATLAB using their previously measured dolphin caudal fins and multiple ordered mathematical approximations of the fin's chord distribution and mid-chord line. This calculation is possible due to the fact that a dolphin fin is extremely similar to a wing. With that said, the dolphin caudal fins are also extremely similar to NACA airfoils in their thickness profiles, as also assumed by Lehigh's researchers. Using this approximated assumption, I was able to draw test pieces on SOLIDWORKS and then print them out using a MakerBot 3D printer. My data collection plan involves running each experiment at different Struhal and Reynolds numbers, and recording the flow visualization at 7 different planar locations along the half span of each test piece. The Struhal number is defined as the frequency of the vortex shedding, multiplied by the panel's chord length, and divided by the velocity of the flow as seen by the pitching panel. The Reynolds number is defined as the density of the fluid, multiplied by the velocity of the flow as seen by the pitching panel, multiplied by the panel's chord length, and divided by the dynamic viscosity of the fluid. Both of these numbers are dimensionless and are displayed mathematically in this presentation slide. I plan to run my experiments at different Struhal and Reynolds numbers by changing 3 parameters. Each parameter will be changed one at a time. First, I will keep all parameters constant while changing only the flow speed between each trial. Next, I will keep all parameters constant while changing only the amplitude of the tip of the pitching panel's sweep. And finally, I will keep all parameters constant while changing the frequency of the pitching motion. All of these changes can be made using the keypad on the water tank and my Arduino code for the pitching motor. My data acquisition technique, PLIF, is executed in the following way. Using the high-speed camera set up below the test section of the water channel, I am able to take up to tens, hundreds, or even thousands of pictures per second of the flow. The major points of interest in the flow are the vortices that are being shed from the trailing edge of the pitching panel, and thanks to the planar laser and fluorescent dye that is induced into the flow, we can highlight the two-dimensional profiles of these vortices very clearly for the human eye and high-speed camera to see. The purpose for experimenting with different parameters is to figure out the most optimal balance between power and efficiency while swimming through water. We can observe power and efficiency by looking at the flow around the pitching panel. A smaller wake behind the panel would mean that there is a lesser amount of pressure drag, which means that the parameters are set up in such a way that the system is more efficient. Additionally, we can look at how long the flow takes to separate from the panel, and a longer period of contact means for a greater amount of skin friction drag. Observing the strength of a wake is more complicated. What does a powerful wake look like? Do larger, more powerful vortices behind the panel mean that the parameters are set up to have the system be more propulsive? We do not have the answers to these questions yet, but Professor Green and her research group are currently working on making observations and interpreting flows to answer such questions. The bendable manner in which aquatic mammals swim does not seem practical for large boats or submarines, but perhaps could be applied to smaller modes of transportation or diving equipment. This is due to the likely possibility that larger vessels will create huge amounts of propulsive force in the water, causing more of a side-to-side motion instead of a forwards motion. My current goal for the near future is to continue collecting data on multiple planes for each caudal fin at various parameters. With that, I will create matrices of these data grids on MATLAB and create multiple 3D composite visualizations of my own, similar to what Professor Green has done. The visualizations will provide a clear representation of the results. Going forward further into the school year, I have a few unlikely yet highly desired research goals. First, I would like to add both heaving and rolling motions to the overall movement of the fin to more accurately replicate how aquatic mammals actually swim. Next, it would be useful to add a skin-like material to the panels for the purpose of reducing skin friction drag. After that, it would be very cool to see how altering the panel geometries with imperfections that act as vortex generators would affect the flow. The purpose of the vortex generation is to promote turbulent flow, which helps delay flow separation from the surface. A delayed surface separation would likely increase skin friction drag slightly, while greatly decreasing the size of the wake or pressure drag. Theoretically, these vortex generators could help the panel swim through water more efficiently. And finally, I would like to eventually move on to shark and whale-shaped caudal fins. Thank you.